All right, so in this section, I'm going to break this into two videos. Sorry about that. In this section, we have quite a bit of information. So now I've already talked about vertices and edges roughly. We have some things to bring in: incident, endpoints, adjacent vertices, connection, vertex edge graphs, parallel loops, circuits, and so forth. So I'm going to make a video that kind of talks about the top section here, and then we'll do a video that kind of talks about our simple paths, Euler circuits, and then Hamilton stuff too. All right, so using this particular slide just to review some of the vocabulary, this would be a great slide to print out, or actually this would be a great slide to put onto your chapter notes that you're going to use. So vertices are, and this is like pretty basic knowledge because you probably have some baseline of vertices. So vertices are points connected by pieces of curves. So remember here we're not doing with straight lines, we can call them curves. And so vertices would be like, for example, X is a vertice, Y is a vertice, W is a vertice, Z is a vertice. And then, of course, we have edges. And so edges would be X to Y would be an edge, E5 would be an edge, E1 would be an edge, and so forth and so on. Even E6, even though it's a loop, would be 1 too. So incident. So, So vertex edge graphs. So, we're going to call them just graphs here, but maybe to delineate, if you have like a pre-text, like kind of pre-college text, to be able to make sure people are thinking about vertex edge graphs versus just graphs in general, that we call them vertex edge graphs. So that's just like a delineation of vocabulary. Incident. So an edge is an incident with U. An edge is an incident with U if the edge is associated with a vertex. And so, like, for example, we could say that E4 is incident with Y because E4 runs into Y. We could say E3 is incident with Y because E3 runs into Y. Y is its endpoint for E3. We could say Z is an incident with, E6 is an incident with Z because E6 ends at Z and so forth. So incident has to do with our endpoint. Adjacent vertices, let me clear my screen real quick. So adjacent vertices would be like, for example, E4 and E5 would be, I said that wrong. Adjacent vertices are vertices, So they're vertices that are connected by an edge. So in this case right here, X and Y are adjacent because they're connected by E4. Or we could say that X and W are adjacent because they're connected by E1. Or we could say that W and Z are adjacent because they're connected by E2. So that's adjacent vertices. Sorry about that, I got parallel mixed up. So parallel would be two different edges and incident with the same vertice. All right, so in this case right here, EF and E5 are parallel because they are incident with the same vertice Y or the same vertice X. So otherwise, though, even though our traditional definition of parallel would be like, for example, two lines that run side by side that are equal distance from each other. So this isn't about equal distance. In vertex edge graphs, it's about sharing a vertice. So sharing Y is what make EF and E5 parallel. Or sharing X is what makes E5 and E4 parallel. All right, a loop. So a loop is like it sounds, pretty straightforward. It has one vertex. So in this case right here, we have a loop because it starts and ends at one vertex. So quick run through of vocabulary. Let's take a look at the next slide. All right, so we have some definitions. The graph G consists of the vertices and edges, a non-empty finite set of vertices, and E, a set of edges with each set associated with a pair of vertices. So this is just vocabulary so that when you see a statement like this, you understand they're talking about that we have a finite set of vertices and a finite set of edges that are associated with those vertices. All right, so we get to use that for the first time. So find two different geometric representations of the graph GVE where V is PQRST, and E is PQPRPSRSRT. So essentially what that's saying is that I already have the answer for you. Like you're already looking at the answer here for this. So what we're saying is that we have vertices PQRST. So PQRST. We have to make paths between or edges between P and Q. So we have a path between or an edge between P and Q. We have an edge between P and R. So between P and R. We have a path between P and S. So path between P and S, R and S, and R and T. And so that's all that is being able to interpret and realize that we have a finite set of vertices that have these particular paths or edges connecting those vertices. All right. On the next one, another option for this could be is that so this is just another way of looking at example one. So in example one, we have the vertices PQRST. In figure 2.b, we have PQRST. And then we have the paths or the edges we need to put in place. So P goes to Q. We have P going to R and P going to S. We have S going to R and we have R going to T. So what the whole idea is that we can interpret. So if I gave you a vertex edge graph, could you identify the vertices and the paths or the edges and list those out? That'll be an assessment piece that you'll have. All right, so taking another look at another example, answer the following questions for the graph in figure 3. Name the vertices that end at E1. The vertices that are endpoints of E1. And so that would be, if you want to hit pause and kind of think about that for a second, you can. So we have E1 is right there. So we have the endpoints of X and W. So check X and W. Name the edges that are both incident with vertex X and incident with vertex Y. And so that would be E4 and E5 because they both end with that endpoint. All right, move this up a little bit out of the way. All right, next one is vertices. Are vertices Z and W adjacent and why? So let's just clear this so we can take a look at it. So Z and W. So Z and W, are they adjacent? And the answer is yes, because the definition of adjacent is that they share an edge. So the answer is yes. All right, last one. Are X and Z adjacent? So here's X and here's Z, and the answer is no. I agree that we could say that there is an adjacency this way, but it has just to be one edge between them, one edge connecting them. All right, some more graph stuff. So once again, just kind of like act like you can't see the solutions down there, and they'll just kind of help this process. Sorry about that. All right, so definition. Let U and V be vertices in a graph, and N be a positive integer. A path from U to V of length N is an alternative sequence of N plus 1 vertices with N edges. So now we're building up to like getting into like this idea of like not looking at simplified graphs or vertex edge graphs. That, you know, we're going to look at this idea of like, when can we apply this to like a more arbitrary situation that'll apply to like everything. All right. And the edge E1 is incident with vertices xi of minus 1 and xi. A path with vertex U to vertex U is called a circuit. This is a circuit. That is, a circuit is a path that begins and ends at the same place. I'm going to hit pause for 1 second. I might want to put this on the other video.